Okay, after all this complex talk on complex physics, this will be a more relaxing talk, but still about complexity of physics, in particular about why physics is difficult to learn and to teach. Okay, so I will consider some aspect of the cognitive, some cognitive aspects of learning and teaching physics, and in particular, we'll try to answer, in some sense, to the questions: why is the study of physics generally considered difficult by many, and if its difficulty is real, it's intrinsic to physics? Well. Let's say high-level physics, I think, is obvious because it's difficult, because it requires a high level of abstraction and also a lot of difficult mathematics. So, but why it works? Okay, but why even high school level mechanics, which deal with everyday facts, with falling bodies, moving bodies, velocity, forces, and require little maths? It's still considered art by many. I think we can put forward, let's say, two hypotheses. The first one is slow thinking. So to solve physics problem, like in math, we need to switch from fast thinking to slow thinking to reasoning. The other one is that, also unlike mathematics, is that physics resembles reality, but with different rule from what we feel. I will explain better this later, but let me do an experiment we did with other colleagues. Here we have a mass SEM, and you are asked, if you want to try to answer, if the acceleration is the same or not in the two cases. Well, the majority of our colleagues in the beginning gave the wrong answer. They say yes, it's the same. Actually, it is not, because here you have also to accelerate the mass m, but and also in this case you have a man who is pulling with a force F box, and this box move with constant velocity v. If I add the second man who pull the box with the same force, what happens? And also here, most physics teachers answer that the velocity is greater, but is constant. Okay, so these are two examples of where also physics teachers fails at the first thought. So we have this interplay of intuitive physics, in the sense that physics is the physics laws that we study at school as to like reality, and on the other hand, there is the need for switching from slow and fast thinking. But let me explain better how works this. What we mean by intuitive physics. All we animals, in particular vertebrates, but also some insects, are born with a basic physical mathematical knowledge. So we have, for example, the ability, since we are almost newborn, but also chicks have the same ability to count count up small integers. And for example, we have the notion of impenetrability of bodies, and so on. The distinction between animate and inanimate. This has been tested by several experiments by Vallortigara principally, and this experiment concern the attention devoted to a particular phenomenon. So, for example, if you expose a baby, you have a phase of habituation where you expose a baby, let's say a sheets of paper with a number of balls. Then he will be surprised if you show him a sheets with an increased number of dots. In some sense, he has already, and the same is true for the impenetrability of body. But what interests us most is that also some physical laws are innate. So, for example, with this experiment, one can show that both children and chicks have this knowledge that if a body fall down, a ball roll and then a while stop, and things that don't start to move by themselves, and if they do, they are animate. So there are some basics laws of everyday physics, of intuitive physics, and these are true also for adults. Let me show you this, for example. If I ask you who is exerting a force here or here, probably you would say that he's exerting the force, and here he's exerting the force. Here you would say that both are exerting the force. For physics, obviously, it's not true, because for the principle of action and reaction, here the wall is exerting a force on the man, and the same is here. Okay, so there is, in some sense, force in intuitive physics is exerted only by intentional beings. Moreover, you have that in the absence of active motors, inanimate objects stop after a while. So if you show, for example, to chicks an object that then doesn't stop after a while, or for example, start to move without a cause, it shows high surprise in the experiment. Is stay to observe the moving body for more time. So these are other. We mainly consider viscous drag, and intuitively we think that larger, heavier objects exert more forces than lighter objects. Okay, and this physics is very similar. This intuitive physics, as shown by in a paper by Rovelli, he showed that basically the Aristotelian physics resemble very much this intuitive physics. So the theory of Aristotle is not wrong in some sense. It is a good approximation for the everyday life physics. And these have also an evolutionary explanation, because naive physics probably evolved to allow us to, or animals, to quickly distinguish between living beings and inanimate beings, because this is a task we carry out much better than solving physics exercise, and these allow us to survive, not now, but in evolutionary history. It's a much important task to solve quickly that solving physical problems. The other aspect I think we play an important role in the learning of physics is the switching between the two systems of thinking. Kahneman shown that there are at least two systems of thinking. If system one, that is fast, is unconscious, it is analogic, and it requires little effort. It is automatic. It is the one used in everyday life to solve everyday tasks. The other one is evolved with language, culture, and formal study, and it's much slower. It's conscious. The other one is unconscious and require a large effort. Okay. There is also this aspect so if solving a physics problem using the fast and unconscious, let's say, system, we are sure to fail substantially. And in fact, there is this test called force concept inventory, which is a a collection of 30 questions based on, let's say, thought to highlight the shortcoming of basic mechanical knowledge, so Newtonian physics, for high school and at university level. And it there are questions formulated in everyday language without math, using a lot of picture to explain both the questions and the answers. These are typical. These are okay. Vediamo, ok. Sì, okay. So these are two typical questions and two typical and possible answers. Okay, it is surprising that this test has been administered by before and after physics class, and again it's relatively small because it is around this is the brown one, so this is around 0.25 the gain in the correct answers, and many concepts, many misconceptions that arise in this test highlight that are very similar to intuitive Aristotelian conception of physics. So many errors are due to the fact that, for example, an object moves until it is pushed by a force, or force is proportional to the potential damage, or is connected, or force still is connected to intentionality. What we did is to, for the moment, we are working on it. We re-elaborate this in a more modern form, and for now we tested the students of the University of Florence, and these are the preliminary results. The students come from almost 520 students. They are all from almost all from scientific disciplines. The majority come from engineering, and we see that the average score is about 10, 11 correct answer, so 1/3 of the total. And here for different categories, different areas of mechanics, we see that it never go beyond the 50%. Okay, so here is a picture of what we do, but mostly Franco Bagnoli has done during the years to teach, to develop new teaching techniques, physics of everyday life, physics and magic, possible interview to the physicists of the past, and so on. I conclude by saying that physics, also mechanics, is difficult because there is this interplay of two, let's say, of these two things: intuitive physics that it's we have to switch from slow thinking to escape from intuitive physics, which gave a rapid answer. So maybe in learning physics, we should try to, we can't eliminate intuitive physics, so we can try to weaken the automatic association and promoting, in some sense, the onset of an alarm bell. Thank you.
Okay. Thanks to the speaker. There are questions?
So I'm curious if you've heard about some sort of study that compares physics compared to other types of subjects. And particularly in a lot of mathematical-based subjects, there's a sort of progression and interdependence of topics. And so the student's performance is significantly hindered in classes that have that progressive format compared to the other types of subjects that are more topical. And so there's a lot more memorization involved and a lot less slow thinking. So you might even think about comparing something that could be topical, like a philosophy class that does require slow thinking, to something like physics, which is much more dependent on your previous mathematical concepts. I don't know if
yes, surely when you have to learn topics, learn a lot of, in some sense, you have to memorize things. This is much easier. But and in fact, for example, other disciplines like earth science, also some aspect of chemistry or biology can be learned very well only by memorizing things. No, philosophy, it's a little bit different, because also there you need slow thinking and reasoning, and I think maybe some aspects of these apply also to philosophy.
There is time for, okay.
Hi, I'm Elke. You know, I'm really interested in the question of gamification, because it seems that as we are dealing with the digital generation, they are especially, you know, involved and savvy of computer games. And so that gamification of different sciences has been very successfully used for pedagogy. So I'm wondering, where is physics in this process of gamification as a pedagogical tool?
Yes, maybe Franco can say something on this. He's working on gamification. I don't know if Franco, you want to say something.
So I'm collaborating with the group of psychologists also. So essentially, they are carrying the part of gamification. I'm developing games at times. And clearly, we haven't so far tested the virtual reality games, but games in general are a way of to invest a lot of cognitive resources in what they're going. So clearly, they can be quite interesting methods, but we were mostly concerned in how to have people that in the university or in the high school pass the physics examination, so they know physics because they have passed the physics exam. But if you ask them something using words that are, or situation which is in the real life and not in the context of physics problem, they use different rules, not what they learned. So essentially, since most of us are physics teachers, we are a little disappointed that we spend a lot trying to convince them that all bodies fall with the same acceleration and so on and so. And then you ask, hey, what if I drop a ball of, not in the physics side, but yesterday I saw a ball rolling down, two balls rolling down the table. What do you think? The heaviest one goes. So this is the idea. The problem is how to let people use the concept that we teach in physics after the end of the physics course.
Okay. We thank again the speaker.